Hey everyone, this is the last benzocoin exam solution video. So I'm going over section 4, question 2, the Oxocarbenium resonance forms question. So here's just the picture of the question. It says, draw the structure of the reactive intermediate formed when the substrate below loses the leaving group in a DN step. Include both significant resonance forms of this intermediate. So basically, how I approached this question was I started by going through each of the side groups and figuring out which one would be the best leaving group. So let's go through that. The potential leaving groups basically are just any of the side groups, not the oxygen that's included in the ring. That would not be a good leaving group, but like the ACHN group, the R group, the hydroxyl group, the OTS, and then CO2ME are all potential leaving groups, but not necessarily all good ones. So a good leaving group is a weak base so that they're able to be stabilized after subsequent protonation, or they just combine with something that has a positive charge. So first of all, the hydroxyl group is a bad leaving group because it's already a strong base on its own. So that's not one that we would want to choose. Any R group, like this one in the equatorial position, it would be a bad leaving group because an R group is just like a carbon group or some kind of hydrogen group. That's not going to be stable on its own with a negative charge. Let's look. Okay, the ACHN group is also a poor leaving group because it's in between the R side group and the hydroxyl group, neither of which can provide a lot of resonance stabilization, especially the R group. The hydroxyl group, if it lost the hydrogen, there could be some chance of resonance, but it still wouldn't be as stabilizing as losing another group. So the best leaving group is the OTS group because it's a weak base and it's in an axial position, which is more unstable than being in an equatorial position, like the CO2ME group. So the leaving group in this scenario is OTS. So right here, I kind of drew out the two resonance structures. So after the OTS group leaves in the dissociation of nucleofuge step, there is a positive charge on that carbon where the OTS group left. And so that is one resonance form. And then there are two lone pairs on the oxygen that's contained within the ring. And so one of those lone pairs, like shown here, can be shifted so that it forms a double bond with the carbon that has a positive charge in this resonance structure, so that the positive charge is on oxygen. So those are the two resonance forms. Basically, I kind of made a stupid mistake when I was doing this question. I put the positive charge on this carbon right here instead of on this carbon, simply just overthinking when the OTS group left. But it's a pretty simple problem when you just break it down. I think the hardest part is really just identifying the good leaving group. So yeah, that's it. Thanks, guys.